Hello students, welcome to this lecture on laws of motion which is included in physics for class 11 as chapter number 5. In chapter number 4, we describe the motion of a particle in space quantitatively. We saw that uniform motion needs the concept of velocity alone, whereas non-uniform motion requires the concept of acceleration as well as velocity. But we have not answered the question as to what governs the motion of bodies. In this chapter number 5, we will answer the basic questions. This chapter includes Introduction to Laws of Motion, Aristotle Fallacy, Laws of Inertia, Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. The topics discussed are very interesting and very important from the point of view of your examination as well as your competitive examinations. So I welcome you once again. Introduction. Some external agency is required to move a body from rest or stop a body from motion. For example, to move a football at rest, someone must kick it. To throw a stone upwards, one has to give it an upward push. A breeze causes the branches of a tree to swing. A strong wind can even move heavy objects. A boat moves in a flowing river without any rowing in it. You can stop a ball rolling down an inclined plane by applying a force against the direction of its motion. Similarly, external agencies like gravitational force and magnetic force can exert force on a body even from a distance, that is, without physical contact. A stone released from the top of a building accelerates downward due to gravitational pull of an earth. A bar magnet can attract an iron nail from a distance. These are the examples and these are the questions and answers. Aristotle's fallacy. The Greek thinker Aristotle held the view that if a body is moving, something external is required to keep moving in it. That is, Aristotle thought that continuous and regular force is required to keep moving the body. The Aristotelian law of motion may be phrased as an external force is required to keep the body in motion. What is the flaw in this? This is not true. What is the flaw in Aristotle's argument? The answer is a moving toy car comes to rest because of external force of the friction on the car by the floor opposes its motion. That is, a toy car moving at the floor is opposed by the friction of the floor. To counter this force, the child has to apply an external force on the car in the direction of motion. When the car is in uniform motion, there is no external force acting on it. The force by the child cancels the force of friction by the force. The corollary is, if there were no friction, the child would not be required to apply any force to keep the toy car in uniform motion. Most of the Aristotelian ideas on motion are now defunct. proved to be wrong and need not concern us. A force is necessary in practice to counter the opposing force of friction. To get the true law of nature for forces and motion, one has to imagine a world in which uniform motion is possible with no frictional forces. This is what Galileo did. The law of inertia. Galileo studied motion of objects on inclined plane. Objects. Number 1. Moving down an inclined plane. Please see the figure on the right hand side. A ball kept on top keeps moving down. This is called acceleration. Moving down an inclined plane accelerate. While those in the second figure, that is this figure, you will see a ball moving up retards. It retards, that is it decelerates. So in the third case, a motion on a horizontal plane continues in motion, that is an intermediate situation between the two. It accelerates, going down accelerates, going up retards, and intermediate situation is continue in motion. Galileo concluded that an object moving on frictionless horizontal plane must either have acceleration or it must neither have acceleration nor retardation. That is, it should move with constant velocity. Another experiment by Galileo leading to the same conclusion involves a double inclined plane. This is a double inclined plane. See, it is a going down and this is a double inclined plane. A ball released from rest on one of the planes rolls down and climbs up the other. If the planes are smooth, the final height of the ball is nearly same as the height. If not, maybe little less but never greater. In the ideal situation, when the friction is absent, the final height of the ball is same as that. If the slope of the second plane is decreased, here you see the slope is more. In this case, in the middle figure, the slope is decreased and the experiment repeated, the ball will still reach the same height. But in doing so, it will travel a longer distance. You see here, it will travel a longer distance. In the limiting case, when the slope of the second plane is 0, that is horizontal here in the third part of the figure, the ball travels an infinite distance. In other words, its motion never ceases. This is, of course, an idealized situation. In practice, the ball does come to a stop after moving a finite distance on the horizontal plane because of the opposing force of friction, which can never be totally eliminated. However, if there were no friction, the ball would continue to move with a constant velocity on a horizontal plane. To summarize, if the net external force is 0, a body at rest continues to remain at rest and a body in motion continues to move with a uniform velocity. This property of body is called inertia. Inertia means resistance to change. Please note, inertia means resistance to change. A body does not change its state of rest or uniform motion unless an external force compels it to change that state. Galileo's revolutionary ideas dethroned Aristotelian mechanics. A new mechanics had to be developed. This task was accomplished almost single-handedly by the scientist Isaac Newton. Newton built on Galileo's ideas and laid the foundation of mechanics in terms of three laws of motion, that is first law, second law and third law. Galileo's law of inertia was his starting point, which he formulated as first law of motion. Every body continues to be in its state of rest or uniform motion in a straight line, unless compelled by some external force to act otherwise. The first law of motion can be stated as: if the net external force on a body is zero, its acceleration is zero. That is, net external force is zero, then acceleration is zero. Acceleration can be non-zero only if there is a net force on the body. Two kinds of situations are encountered in the applications of this law in practice. In some examples, we know that the net external force on the object is zero. In that case, we can conclude that the acceleration of the object is zero. For example, a spaceship out in interstellar space, far from all other objects and with all its rockets turned off, has no net external force acting on it. Its acceleration, according to the first law, must be zero. That is, A should be zero. If it is in motion, it must continue to move with a uniform velocity. For example, a book at rest on the table. It is subjected to two different external forces. The force due to gravity, that is weight acting downwards. Please see the figure on the right hand side. Weight is acting downwards and normal reaction is acting upward on the book by the table. This which is represented by the letter R, and W is the weight of the book which is acting downward. R is a self-adjusting force. This is an example of the kind of situation mentioned above. The forces are not quite known, but not known fully, but the state of motion is known. We observe the book is at rest. Therefore, we conclude from the first law that the magnitude of R equals that of W. A statement often encountered is: since W is equal to R, forces cancel and therefore the book is at rest. This is incorrect reasoning. The correct statement is: since the book is observed to be at rest, the net external forces on it must be zero, according to the first law. This implies that the normal force R must be equal and opposite to the weight W. Consider another example: a car moving with a uniform velocity as shown in figure B here on the right hand side. This car picks up speed and then moves on a smooth straight road with uniform speed. When the car is stationary, there is no net force acting on it. During pickup, it accelerates. This must happen due to a net external force. Note, it has to be an external force. The acceleration of the car cannot be accounted by any internal force. This might sound surprising, but it is true. The only conceivable external force along the road is the force of friction. It is the frictional force that accelerates the car as a whole. When the car moves with a constant velocity, there is no external force. This property of inertia contained in the first law of motion is evident in many cases. So we go on to define inertia. Inertia is the property of the body due to which body opposes the change in its state, and hence greater is the inertia. Inertia is proportional to the mass. Heavier bodies have greater inertia and lighter bodies have the lighter inertia. Different types of inertia. Inertia of rest. It is the inability of a body to change its state of rest. For example, when we shake a branch of a mango tree, the mangoes fall down. Another example is inertia of motion. It is the inability of a body to change its state of motion. For example, when a bus or a train stops suddenly, a passenger sitting inside tends to fall forward. The third one is the inertia of direction. It is the inability of a body to change its direction of motion. For example, the wheels of a vehicle throw out mud when they are rotating. Mudguard over the wheels stops this mud. Momentum. The total quantity of motion possessed by a moving body is known as the momentum of the body. It is the product of mass and velocity. Momentum is represented by letter small p, which is equal to m mass into velocity, that is mv, where m is the mass and v is the velocity. The concept of momentum was introduced by Newton to measure the quantitative effect of force. That is, quantitative effect of force is measured by the concept of momentum. We'll continue our discussions on first law of motion by solving a numerical problem. Question number 1. An astronaut accidentally gets separated out of his small spaceship which is accelerating in interstellar space at a constant rate of 100 meters per second square. What is the acceleration of the astronaut the instant after he is outside the spaceship? Assume that there are no nearby stars to exert gravitational force on him. That is, the gravitational force on the astronaut is 0. Answer. Since there are no nearby stars to exert gravitational force on him, the small spaceship exerts negligible gravitational attraction on him. Thus, the net force acting on the astronaut once he is out of spaceship is 0. By the first law of motion, acceleration of astronaut is also 0. Momentum. Momentum is a vector quantity and is given by the relation small p is equal to m into v, vector v, where p is the momentum and m is the mass and v is the velocity or speed. The importance of momentum are revealed by the effect of force on motion. What is the effect? So its importance is due to the effect of force. So let us give some examples. A small car and a heavy vehicle parked on a horizontal road. So it is very difficult to push a heavy vehicle as compared to the small car because its weight is more. Example 2. A greater opposing force is needed to stop a heavy body than a light body in the same time. So a greater weight, a body having a greater weight needs more force. Example 3. If two stones, one light and the other heavy, are dropped from the top of a building, a person on the ground will find it easier to catch the light stone. It is easy to catch a light stone than heavy stone. The mass of a body is thus an important parameter that determines the effect of force on its motion. Another factor apart from mass is the speed. To consider the momentum. For example, a bullet can easily pierce a human body before it stops. But if the same bullet is fired with a slower speed or a moderate speed, it will not cause that much damage. Thus, for a given mass, the greater the speed, the greater is the opposing force. Combining both speed and mass, the product of mass and velocity is the momentum is evidently variable of motion. The greater the change in momentum in a given time, greater is the force that needs to be applied. For example, we have seen a cricketer catching a ball. A seasoned cricketer judges the speed of the ball very easily as compared to a new entrant or a novice. A new novice hurts his hands because he is not able to judge the speed of the cricket ball. Thus, the force not only depends on the change in momentum but also on the speed, that is, how far the change is brought about. With the basic knowledge of momentum, we now proceed to state the Newton's second law of motion. Newton's second law of motion states that the rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction of the in which the force acts. We know that momentum is equal to vector P is equal to m into vector V. Let it be equation 1. Thus, if under the action of a force vector F for time interval delta t, the velocity of a body of mass m changes from v to v plus delta v, its initial momentum p equals mv changes by delta p is equal to m plus delta v. According to the second law, F is proportional to delta p by delta t, or F is equal to k into delta p by delta t, where k is constant of proportionality. Please note here F is a vector and delta p are vectors, and that is why an arrow is put on their respective heads. Taking limit as delta t tends to 0, delta p by delta t becomes differential dp by dt. Therefore, F is equal to k into dp by dt. Let it be equation 2. For a body of fixed mass m, dp by dt is equal to d by dt of mv, because we know P is equal to m into V. Therefore, that becomes, because mass is constant, is equal to m into dV by dt. That is, dV by dt is acceleration. That is equal to m into A, vector A. Let it be equation 3. That is, the second law can also be written as F is equal to K into MA, where F is the vector force is equal to K constant, M constant, that is the mass of a body, and A is a vector. Let it be equation 4, which shows that the force is proportional to the product of mass and acceleration. Now we will define unit of force. From the second law of motion, we know that F is equal to K into MA, that is equation 4, as per the equation 4. Then for simplicity, let K is equal to 1 and then F is equal to MA. If you put K is equal to 1 in this equation, F is equal to M into A. Let it be equation 5. If k is equal to 1 and m is equal to 1 kg, mass is equal to 1 kg and acceleration is equal to 1 meters per second square, then F becomes F is equal to 1 in this equation. So now with this we will define the unit of force. In SI unit of force, the is Newton. That is, Newton is a force, unit of force in SI unit. Therefore, 1 Newton is equal to 1 kg meter per second square, which causes an acceleration of 1 meter per second square to a mass of 1 kg. Important points about the second law. When F is equal to 0, then A is equal to 0. The second law is obviously consistent with the first law. The three components of vector F along x, y and z axis can be stated as Fx is equal to dp of x by dt, that is equal to max. So where F is the F force along x-axis, P is the momentum along x-axis and A is the acceleration along x-axis. Similarly, if you take the components along y-axis, Fy will be equal to d by dt of Py, that is equal to m into Ay, and the component of force along z-axis will be Fz is equal to d by dt of Pz, that is equal to m into Az. That means if a force is not parallel to the velocity of body but makes some angle with it, then it changes only the component of velocity along that direction of force. The component of velocity normal to the force remains unchanged. For example, in the motion of a projectile under vertical gravitational force, the horizontal component of velocity remains unchanged. F refers to the total external force along the system, and A refers to acceleration of the system as a whole. Any internal force in the system is not included in F. The second law of motion is a local relation, which means the force F at a point in space and at a certain instant of that time is related to acceleration at that point and at that instant. Acceleration is determined by the force there, not by any history of motion of particle. For example, the moment after a stone is dropped out of an accelerated train, it has no horizontal acceleration or force if air resistance is neglected. The stone carries no memory of its acceleration with the train a moment ago. Let us solve some problems on Newton's second law of motion. Question number 2. A bullet of mass 0.04 kg moving with a speed of 90 meters per second enters a heavy wooden block and is stopped after a distance of 60 centimeters. Please note 60 centimeters. What is the average resistive force exerted by the block on the bullet? So let us understand the concept. Concept is a mass of 0.04 kg is moving with a speed of 90 meters per second. and it enters a heavy block and is stopped after 60 centimeters distance. So we have to calculate the resistive force exerted by the block on the bullet. Answer. Given V, the final velocity stop means it is stop final velocity V equals 0 and initial velocity is moving with a 90 meters per second. U is equal to 90 meters per second and the distance traveled is 60 centimeters. This 60 centimeters has to be converted into meters. Okay, that is equal to 60 centimeters divided by 100 is equal to 0.6 meters. And now we have to find the retardation and resistive force. We know that formula V square is equal to U square plus 2AS, where V is the final velocity, U is the initial velocity, and A is the acceleration, and S is the distance traveled. Substituting, we get and rearranging A is equal to V is 0. So minus U square goes to the left, minus U square divided by 2S. This is the rearranged formula, that is equal to, substituting, we get minus 90 into 90 divided by 2 into 60. S is 60. That is 2 into zero point 0.6. 2 into zero point 0.6. That is equal to minus 675 meters per second square. From the formula, we also know that F is equal to m into A. That is, force is equal to mass into acceleration. We get F is equal to, mass is 0.04 kg and acceleration is minus 675 meters per second square. That is equal to, substituting, 0.04 into minus 675 and multiplying, we get that is equal to 270 kg meters per second square or Newton. This capital N is Newton. The actual resistive force and therefore the retardation of the bullet may not be uniform. The answer therefore indicates the average resistive force. Next question. Question number 3. The motion of a particle of mass m is described by the equation y is equal to ut plus half gt square. Find the force acting on the particle. Now we have to understand the concept. So the motion is a y, means it is a vertical motion. Y is equal to u is the initial velocity into t is the time plus half g is the acceleration due to gravity, t square. Find the force. From this equation, we have to derive the formula for force. We know that y is equal to ut plus half gt square. That is the formula for distance. Differentiating, we know velocity is equal to distance traveled over time, or v is equal to dy by dt. So differentiating, so we have to find dy by dt. For that purpose, we have to differentiate this equation 1. We get dy by dt is equal to u into differential of dt by dt, that is 1. That is equal to u only, plus half g is the acceleration due to gravity, that is constant, into differential of t square, that is 2t. Therefore, v is equal to dy by dt is equal to this, simplifying this right hand term, we get u plus these two and these two get cancelled, u plus gt. Let it be equation 2. Now we have to calculate the acceleration. Acceleration is given by the relationship a is equal to dv by dt. That is, acceleration is equal to differential of velocity over time. Let it be equation 3. Now differentiating to find dv by dt, we get dv by dt is equal to, here d by dt of u plus gt, that is equation 2. Therefore, we get du by dt is 0, d of gt by dt is g, that is equal to g. Therefore, A is equal to g. Now we have to find the force using the relationship F is equal to m into A. Therefore, now we find A is equal to G by equation 4. Substituting for A, we get F is equal to m into G. Thus, the given equation describes the motion of a particle under acceleration due to gravity. And in this equation, y is the position coordinate in the direction of G. In section 5.6, we will study about the Newton's third law of motion. Before we take up Newton's third law of motion, let us understand the term impulse. A large force acting on a short time. A large force acting for a short time to produce a finite change in momentum is called impulsive force. Impulse is equal to force into time duration. That is equal to impulse is nothing but change in momentum. Now let us give an example wherein a batter hits bat a ball straight in the direction of the bowler without changing its initial speed of 12 meters per second, and if the mass of the ball is 0.15 kg, determine the impulse imparted to the ball. Assume linear motion of the ball. Let us answer this. Change in momentum is mass into velocity. So, initial momentum is 0.15 into 12, that is weight into velocity, that is given, minus it is deflected back in the same direction without change in initial speed. Therefore, it is minus of minus 0.15 into 12. So, change in momentum is 0.15 into 12 minus into minus of 0.15 into 12. That is equal to minus into minus becomes plus and it's add up. So, therefore, the answer is 3.6 Newton. Therefore, impulse is equal to change in momentum is equal to 3.6 newtons in the direction from batter to the bowler, because the batter hits it back. Now let us study Newton's third law of motion. Statement: to every action there is equal and opposite reaction. So, important points of third law of motion are: forces always occur in pairs. Force on a body A by body B is equal and opposite to the force on the body B by A. There is no cause-effect relation implied in third law. The force on A by B and the force on B by A act at the same instant. Point number 3. Action and reaction forces act on different bodies, not on the same body. Consider a pair of bodies A and B. So, vector A to B, that is the force A to B, is equal to minus of vector force by B to A. However, if you are considering the system of two bodies as a whole, f of AB and f of BA are internal forces of a system A plus B. They add up to give a null force. Internal forces in a body or a system of particles thus cancel away in pairs. These are the few important points connected with Newton's third law of motion. In the next slide, we will discuss some of the work examples on Newton's third law of motion. Two identical billiard balls strike a rigid wall with the same speed but at different angles and get reflected without any change in speed, as shown in figure below. Question is, what is the direction of force on the wall due to each ball? And part B, part 2 is the ratio of the magnitude of impulses imparted to the balls by the wall. Two figures are shown here. Let us understand the concepts of the problem. So the ball strikes at the wall at a horizontal, a case A, and it gets deflected in this direction. So it strikes in this direction and reflected back in this direction. And part B, it strikes at angle 30 and gets reflected in this direction. So we have to find the direction of force on the wall. The direction of force in both the cases is normal to the wall because wall is vertical and vertical in this part and the force is normal to the wall. Therefore, in both A and B, the direction of force is same. To find the force on the wall, consider the change in momentum by applying second law of motion. Now we have to consider the second law of motion. Case A. Let us take this case A. Here the ball strikes the wall. So Px initial is, if you take x positive direction of this, Px initially is m into u, mass into velocity, initial velocity u, and vertical component is 0, Py is 0. And final, after reflection, that is, it comes back in the opposite negative direction. Therefore, Px final will be equal to minus of mu. That is, and Py is 0 as there is no vertical component of momentum. Let it be equation 2. So impulse is the change in momentum vector, that is equal to 1 minus of 2, that is equal to mu minus of minus mu, that is equal to 2 mu. Therefore, y component of impulse is equal to 0. Py is 0, final, initial, both initial and final are 0. Therefore, y component is 0. Therefore, impulse and force are in same direction. Impulse and force are in same direction because both are positive. Thus, the force on the ball due to wall is normal to the wall along negative x direction. See here it is in the negative x direction, equal and opposite. Using Newton's third law of motion, force on the wall due to ball is normal to the wall along the x positive direction. So the force on the wall due to ball is in positive direction and due to wall on the ball is in negative direction. Case B. Here it is incident at an angle 30. We have to take the split this vector, that is, this is the force on the of the ball on the wall. This incident we have to split into two components. So the x component is in positive direction and y component is in the negative downward. So therefore a px is equal to Px initial is equal to mu cos 30 and Py is equal to minus mu sine 30 because it is in the negative direction. Let it be equation 3. Then P final, so it strikes the wall and gets reflected here at an angle 30. So it is minus of mu. You split it, the deflection is Px will be in this direction. That is negative x. That is why it is minus mu cos 30 and it is negative once again. Downward here. Here also it is downward. Therefore, it is my Py is equal to minus mu sine 30. Let these two equations be equation 3 and equation 4 respectively. Impulse in the change of momentum vector is 3 minus 4. Therefore, x component is mu cos 30 minus of minus mu cos 30, that is equal to 2 mu. It becomes minus of minus becomes plus 2 mu cos 30. Therefore, y component here minus mu sin 30 minus of minus is plus. Therefore, y component gets cancelled and x component gets added up. Therefore, impulse and forces are in the same direction. To find the ratio of magnitude, we have to divide 2 mu by 2 mu cos 30. Therefore, it is ratio of magnitude is equal to 2 mu by 2 mu cos 30. 2 mu and 2 mu get cancelled. 1 over cos 30, that is equal to 1 over root 3 by 2, that is equal to 2 by root 3, that is equal to 1.2. With this, we come to the conclusion of first part, that is sections 5.1 to 5.6 of laws of motion. In the next lecture, we will study conservation of momentum, equilibrium of particles, common forces in mechanics, circular motion, and we will also solve problems in mechanics. Till then, goodbye.